Right, hello Year 12. So, it's going to be a shorter one than last time because we're looking at resultant forces, which really hasn't developed much from what you did in Year 11. You'll have to apply this to more complicated situations, and that's what we're doing in our problem solving session on Monday. But for the time being, you've actually probably got quite an easier homework because there's no new concepts here really. So you'll remember from Year 11 that gravitational force was equal to the mass times the local strength of gravity, and you'll remember that when an object was accelerated, force equaled mass times acceleration. Unit of force was newtons, unit of mass kilograms, unit of acceleration ms to the -2, and that's the same here. We've got newtons, kilograms, meters per second to the -2. This equation deals with the force something will feel when it's falling due to gravity. This equation explains the force needed to cause a mass to accelerate. Typically this is applied to cars, planes, mechanical objects in exam questions, whereas this is falling objects. What we want to do first of all, and this isn't essential, I think it's really interesting, is combine these two equations and see what happens when the force that's causing something to accelerate is gravity. So if we drop something, if we have a falling object, and for a second we're going to forget about being physicists and we're going to remember that air resistance exists, we've got mg, the force due to gravity, minus Fr. This one here is our air resistance. That's our force due to friction with the air, is equal to ma. So what we want to do here is simplify this, move our mg to the other side. We end up with, well, move our ma to the other side and Fr here. We end up with mg minus ma equals Fr, and then simplifying this, we end up with Fr equals m g minus a. Now sometimes we talk about things being a universal law of physics that is always, always, always true. This applies to objects falling through a viscous atmosphere. If we were to say falling through a vacuum, Fr would be 0, G and A would be identical. Our acceleration due to gravity is going to be smaller because of this Fr. Now if we think about it, as you go faster, you hit more air particles. That means Fr will get bigger. If the friction due to air resistance is getting bigger, something has to change on this right hand side. The mass of the object can't change, acceleration due to gravity can't change, so the actual acceleration will get smaller. So the faster you go, the bigger your air resistance gets, the smaller your acceleration gets. A sub-challenge, if you're feeling clever, and a handful of you should do this, is to try to rearrange this equation for A, and on Monday first thing explain to me how it shows how A changes when Fr changes. That's a little challenge for you. But for the rest of us, we're happy to know if air resistance is bigger, acceleration due to gravity is smaller. If we forget about air resistance and we consider things in a vacuum, then we end up with mg equals ma. M's cancel. Your acceleration is due to the strength of gravity. Reason being, the more massive you are, the bigger the force of gravity, but the more massive you are, more force is needed to accelerate you, is needed to push you. They always balance. Interesting thing, and we never get to do this even in Year 13, is the mass here technically is the gravitational mass. That's the mass that's affected by gravity fields. This mass here is the inertial mass, and that's the mass that it tells us how hard it is to get something going, how hard it is to make something move. And there's no reason in any equations, there's nothing in physics that says inertial mass and gravitational mass should be the same. They are, they're identical to as many decimal places, as many significant figures as we can measure. We've always found that inertial mass and gravitational mass are the same value. There's no reason why they should be. There's some symmetry, there's some underlying symmetry, some underlying issue in physics that's cropping up here that as yet I don't think we truly fully understand. How you would have to apply this in an exam question is to talk about why objects have a top speed. Air resistance increases, acceleration decreases. When A reaches 0, you can't get any faster, your forces are balanced. You may have to do a calculation. If you look at the pages in the textbook I asked you to, we're going to do one of the summary questions, the one with the car. It says that there is a force of the engine of 550 newtons and friction and air resistance are equal to 330, and it wants to know the acceleration. So rearranging for A, we end up with F over M. We know that our mass is 800 kilograms, must be quite a small car. We know that the force from our engine is 550, and now we need to ask ourselves, is the force due to frictional and air resistance? We know it's 330, but is it added or minus? It's picking the signs that are important here. And what you've got to ask yourself, is this force making it go faster, or is that force making it go slower? If the force is making it go faster, Formula 1 fans, if this was force due to the KERS unit, the kinetic energy recovery system, that's going to be added. It's an extra force that's making it go faster. If it's friction, if it's air resistance, if it's anything like that, it's going to be minus because it's slowing it down. So we're ending up with 220 over 800, which gives us an acceleration of 0.275 ms to the minus 2. Let's check out. We started with 1, 2, 3 sig figs. 1, 2, 3, 1, 2, 3. These are measured zeros. We started with 3 significant figures. We finished with 3 significant figures. I think we're happy. So, have a look at the pages I asked you to in the textbook. Try and do the other summary questions. And I'll see you Monday morning for our problem solving class. Okay, thank you.